One of the major advances in computing that's been done recently is the advent of quantum computing. And uh, it, it poses certain difficulties as well as advantages, and that is the superposition of the quantum states can are not completely stable and can lead to what appears as a bit error in your computation. Um, we have a group here that's working on quantum computing error mitigation. The idea is to be able to reduce the bit errors and, in fact, improve the reliability of quantum computing. So I will let the guys take it off and explain how it's done, and the gal.
Hi, my name is Pranav.
My name is Rohan.
My name is Dia.
And we're from the ASDRP McMahon Lab. So beginning in with our first piece of information, we talk about the classical 3-bit error correction approach that's been being used. So when sending information through a wire, sometimes bits flip like so, 0 to 1 and 1 to 0. In order to mitigate this issue, there's a simple protocol that's been used. Step 1, designate 3 bits to represent that 1 bit of information that we're talking about. And redundancy is usually a theme here. For example, 000 can be shown to represent 1 bit of information. That's the first step. And for the second step, we can send this bit of information through a wire. And if a bit is flipped, you can simply correct it through a process known as majority voting. For example, 000, if that was a bit of information, and it turned out to be 010, you can see that the middle bit has been flipped, so that can be corrected. Using a classical approach, there would be an issue, because notice that if there had been 2 errors, the
Classical
algorithm.
3-bit error correction. What is this?
I want to continue. So we'll get to questions after, but the algorithm would have corrected it the wrong way. So continuing on, the next slide. The quantum 3-bit error correction that some of our researchers talked about is relating to bit flip error, where similarly through a classical 3-bit, we introduce redundancy into a qubit, where we can write it out in the form of A ket 1, as defined by this notation, plus B ket 0 to represent superposition. So, adding redundancy, the new notation of this qubit becomes A ket 111 plus B ket 000. If there's a bit flip, the output would be one of these 3 states. A ket 011 plus B ket 100, and so on, as shown in these other states. Continuing on, we talk about service codes.
So a big problem with the previous method is that if there were 2 errors in the 3-bit error correction code, they would be corrected to the wrong bit. So there is this family of codes called surface codes, which fixes this issue. Surface codes are robust against errors and have a higher threshold of error than other methods, and they're more practical to implement. So what are surface codes? They are basically a bunch of qubits that are embedded into a 2D lattice that represent one logical qubit of information. They do this by being entangled to each other and interacting primarily with its neighbor. So errors are detected with these operators called stabilizers over here. And in the real world, you use this thing called ancillary qubits to detect errors in the um, jurisdiction of these operators. So how do they detect errors? Well, they detect the parity of each qubit with all the other qubits under its jurisdiction. They do this because if they directly measure the qubit, the whole point of having the qubit in superposition would be really there would be no point because the superposition would collapse once the state is measured, and the entanglement would also collapse once the state is measured. So, another property of the surface code is that errors, when introduced to the surface code, they propagate around the surface code as shown over here. These red lines represent errors that are detected by this operator, which is called a vertex plaquette, vertex stabilizer. And the ones on the faces over here, they are called Z Pauli errors, and they're detected by this plaquette stabilizer over here. So let's take this as an example for a series of errors that have been injected into the system, where this is the start and this is the end. We can see that there is a line of errors between the two start and end points. However, what the stabilizers see is only the start and end point, and they can't even see which one is the start and which is the end point. So what we have to do is go in there and draw out the errors in between the start and end points. So as you can see, there are multiple ways to connect these kinds of errors with only knowing the start and end point. With these X errors, there is one way like this and another way around the whole thing. Now imagine if there are 10 of these kinds of errors scattered around. There would be some overlap and it would be really complicated. So our goal over here is to use graph neural networks to decode error syndromes under a bosonic bath. And a bosonic bath will be discussed here. So what is a bosonic bath? It's basically a large collection of bosons, which are particles like electrons that surround a system of interest, which is over here the surface code. Bosons can exchange
basically
the
dancers, like a lot of
system in
classical dance were
various
inverted
quantized
past
ways
part
called bosonic modes. And by exchanging energy, they just inject error into the system because they change the quantum state of the qubit, which is really important because the quantum state is the thing that holds the information. And bosonic baths, they wreak havoc on the surface code by introducing pattern and correlated noise, which standard methods cannot identify because standard methods only analyze individual qubits and their immediate neighbors. So by affecting multiple qubits at once, bosonic baths, they push the surface codes to their absolute limit, to their threshold error rate, making the correction less reliable and putting all the data that you've encoded, just that data would be lost. And now we'll discuss the way we are proposing to decode these errors.
So now let's go into what a graph neural network is, first in general, and then as it applies to our project. So let's start with what is a graph. A graph is a way to represent information. So essentially another data structure, just like a list or something. But these are more complicated. They can include nodes or vertices, which are the blue dots that you see on the diagram representing, as well as green edges or links. These represent connections between different nodes. So there are probably many real-life examples that you could think of that could actually be modeled by a graph, even though you might not know it, such as social networks. Imagine every person was a node or vertex, and then each green line was a connection between people, like a friendship, for example. Or this could be used in geographical mapping, especially for roads and such. If each destination was a node and each path between the destinations was an edge, you could apply algorithms to find, for example, the shortest path between 2 points. On a much smaller scale, these can also be used to represent the structure of DNA and proteins. Finally, they can also be used to represent internet architecture. This one might be a little bit harder to see, but imagine that each node or vertex was a web page, and each green edge was a kind of a link that takes you from one web page to the next. Now, these graphs can be used in convolutional neural networks. So typical convolutional neural networks, for example, on a picture, they will look at each pixel and the pixel surrounding it. to make predictions about this graph. In a graph, however, they will use information about each node and the nodes surrounding it to make a prediction. So here is a sample architecture of what a graph neural network might look like. It gets the graph as an input, and then the hidden layers are trained to recognize different information about each node and edge. Then typical activation layers are applied until finally it reaches an output. These outputs can come in the form of node level predictions, which will make a prediction about each node, or an edge level prediction, or a single prediction about an entire graph. And now Pranav will be talking about how this relates to our project.
So talking about more information regarding this, we want to basically represent units of quantum computing, also known as qubits, as graph nodes. And then we can also represent operations between qubits as graph edges. So we can use annotated data collected in previous steps discussed in the slideshow to make edge level predictions about which computations are likely to result in error and how we can solve them, increasing our effectiveness. We can also use graph properties to determine how this error is likely to spread across different qubits. Furthermore, we want to use precise detection as a key first step to this error correction problem, which has the benefit of being one of the major opportunities for improvement in the current quantum computing space. The next couple of slides are just sources and a bibliography that we resourced. And we want to thank Dr. McMahon and ASDRP, as well as thank you for listening. And we want to see if you guys have any questions.